there, this is Chris Clements here with another Chemistry to Go on Chem Podcast. This one will be on kinetics, which are also noticed as reaction rates. So let's go ahead and get started. You will have an enhanced podcast as usual, and if you wish to load the PowerPoint on your own, that's fine, but you can certainly go to different points in this enhanced podcast if you need to. Alrighty. So, kinetics deal with movement. The prefix KIN definitely reflects the word movement, as in kinesiology. It's the study of muscle movement, for example. My dad taught kinesiology for a long time, so I got to learn a lot about that. So let's first talk about change and how we express change, because we're looking at the rates of reaction, meaning how things change with respect to time is what we'll actually look at. So let's look at a couple of just everyday type changes. And if we say the ice melted or the nail rusted, how would we express those changes as a rate, meaning something over time? Well, how would you describe to me how the ice melted? If you think about that, you might measure the volume of water that was produced, for example, from the ice's melting. And you might tell me that you would express that change as milliliters of water that formed every minute or, every hour or something like that. The nail rusted. You might think that it could be something such as how many grams of iron 3 oxide were produced every week, or perhaps longer time frame in there, but the idea being that mass changes as opposed to volume change. So what we need to learn how to do is express change, and we're going to be looking at expressing change in a reaction rate. And change in a reaction rate is always something divided by a change in time. And what we look at is a change in the amount of reactant divided by a change in time. As a reaction occurs, we need to think about what happens to the amount of reactant. Remember that reactants are always written on the left and products are always written on the right. And as a reaction progresses, what happens to that reactant? Well, you should be able to answer that question with the reactant amount goes down as the reaction occurs. Well, if it's a one-way reaction, it does a different thing than it does if it's a two-way reaction. We'll get to that in a moment, so I don't want you to get that far ahead of me. But when we express the rate of reaction, we need to look at it as a change in the reactant amount, since we know that reactant amount will change with respect to the change in time. So we write a rate of reaction formula as rate equals the opposite of the change in reactant amount divided by the change in time. The rationale for that negative sign in the front is that in chemistry land, people apparently don't like negative numbers, just arbitrarily placed. So when we say a change in reactant amount, we need to understand that the reactant amount will decrease. And to get a change, we would do final minus initial, which means that we would end up getting a negative value because our final amount is less than our initial amount. Well, again, chemistry land folks don't like negative numbers when they don't need to be there, so we just take the opposite of that negative number and we're guaranteed to always have a positive rate. Rates are always positive, just telling you that. Alrighty, so if you look at a reaction that I have here that is solid magnesium reacting with hydrochloric acid to produce magnesium chloride in aqueous phase and hydrogen gas. You might have seen this reaction before. You definitely have if you have me for Chemistry 1. You did a little experiment where you reacted magnesium metal with hydrochloric acid and it produced some hydrogen gas, and you measured the volume of hydrogen gas and proved molar volume to me. Little aside there. So when we look at this reaction, we look at the mole to mole to mole to mole ratio, we see that the rate actually remains the same on left and right side, but the formulas change. I want you to notice that there's a 2 in front of the change in change in time for the HCl, and that's because there are 2 moles of HCl. And notice that we have negatives in front of the change in moles of magnesium and change in moles of HCl, but we don't have negatives in front of the change in moles of magnesium chloride or the change in moles of hydrogen. That's because they're products, and we know that as time progresses, their amounts will increase. So when we do final minus initial, we'll get a positive change, and we don't need to make it negative to fix the chemistry land honor code of no negatives arbitrarily. So When we look at a one-way reaction, we are only going to determine the reaction rate by looking at the reactants. The reactants' reaction rate will actually decrease as time progresses. Would you think about why? Think about what eventually happens to the amount of reactant in a one-way reaction. Well, as time progresses, the reaction rate will decrease because there's less reactant there, and eventually you're going to run out of reactant if it's a one-way reaction. When we look at a reaction rate of an equilibrium reaction, we again only look at it from the viewpoint of the reactants. And yes, the rate of reaction will decrease as time progresses, but what eventually happens to that rate? Does the reaction ever really stop? You should be able to think through that and realize, okay, it's an equilibrium reaction, it will reach equilibrium, it has those reversible arrows in it, which means, the reactants turn into products, and then when there's enough product to get sated, they turn around and make reactants, and then the whole thing goes back and forth, and gee, it never really stops. So no, the reaction doesn't stop. And what eventually happens to the rate of reaction is that the forward rate of reaction, when reactants turn into products, will equal the reverse rate of reaction. It's a very key point in kinetics. So if we look at the reaction of the decomposition of nitrogen dioxide, we've noticed that it produces nitrogen monoxide and oxygen gas. And when we balance the reaction, we have 2 moles of NO2 gas yielding 2 moles of NO gas and 1 mole of O2 gas. Notice that it is a reversible reaction, which means it will not stop. It means that the rates of forward and reverse reaction will eventually become static. So if we look at this reaction rate graphically, with time as our independent variable on our x-axis and the concentration of the reactants and products in moles per liter as our dependent variable on our y-axis, we should be able to see that the concentration of NO2 goes down with respect to time, and the concentration of NO goes up with respect to time. Notice on this graph that the concentration decrease of NO2 is simply the reflection of the increase in NO. It's because their mole-to-mole ratio is 2 to 2 or 1 to 1. The O2 increase in concentration is approximately half that of the NO increase. That is because the mole-to-mole ratio of NO to O2 is 2 to 1. Now, I did not extend the time enough on this x-axis for you to see that the rates will eventually equal each other, but graphically what that would mean is all 3 of these lines would be parallel to each other, so that, again, our forward rate equals our reverse rate. Let's talk about a few necessities of reaction. One of them is proper orientation. That is, reacting molecules, atoms, ions need to be properly spaced to be able to react with each other. Now, who knows what that proper space is? I guess they do, because I really don't know how to tell you how we know what the proper orientation is. I'm just either not that knowledgeable or we don't know how to tell. But if I look at the reaction of 2 moles of HI becoming H2 and I2, and I give a representation of the 2 moles of HI as you see on the left here, oriented as you see it, then any other orientation is a no-no. So hence you have your no symbols there. Another necessity of reaction is that a set of reactants must have sufficient energy. You most likely have looked at this before in your chemistry class. Definitely my students have. And that sufficient energy is known as activation energy, written as uppercase E with the subscript of A. You've probably seen a curve like this where you have reaction progress or time on your x-axis and energy on your y-axis. In this particular reaction, HI starts out as our reactant with a specific amount of energy. It climbs the hill to become an activated complex. The difference in energy between the apex of the hill and the beginning point is our activation energy. And in this particular reaction, the products have less energy than the reactants, so when I subtract the reactants energy from the products, I will end up getting a negative value, which tells me this is an exothermic process. But the thing I want you to realize here is that every reaction has to have sufficient activation energy to be able to progress. Some factors that affect the rate of reaction are concentration, temperature, surface area, the presence of a catalyst, and the rate determining step. And I'm going to explain a little bit and give an example on each of these. Concentration will affect a reaction rate. If we have an increase in concentration of reactants, we will have an increase in reaction rate. If we have a decrease in concentration, we'll have a decrease in reaction rate. I want you to think of the concentration of oxygen. I think you've all seen oxygen tanks around and seen the signs that say no smoking around it. Well, that would be because combustion requires oxygen to take place, and that combustion reaction will be vastly accelerated, meaning its reaction rate will be increased in the presence of 100% O2 versus 21% O2, which is what air contains. Temperature will also have an effect on reaction rate in that an increase in temperature increases the reaction rate. So an example of that would be paper. We know always reacts with oxygen and air. I think you might have some papers on your parents' refrigerator that is browned. That means that it has been oxidizing since your kindergarten days when you first made that lovely piece of artwork. And that means we can state that as temperature goes up, our reaction rate goes up. Surface area also plays a role, obviously. When we increase surface area, such as, let's see, we have sawdust compared to a block of wood. Which one do you think will burn more quickly? I hope that you say the sawdust, because it certainly will. And the presence of a catalyst. Now, a catalyst is a totally different concept here in that it does increase reaction rate, but it does so by a very different mechanism. We're going to talk about the mechanisms in just a moment. So an example of a catalyst would be the enzymes in you, for example. It would take you a very long time to digest all of that food that you put in you without the enzymes that you have. An example of a non-biological catalyst is using manganese 4 oxide to accelerate the decomposition of hydrogen peroxide. If I drop some manganese 4 oxide into a 30% solution of hydrogen peroxide, I get this lovely genie in a bottle kind of effect that produces decent enough heat to actually turn the water that is a product into steam. So it's pretty cool looking. And, you know, if I were doing vodcasts, I'd be showing that to you right now. Oh, well, you get to perhaps Google H2O2 decomposition, see what you can find. Then the last thing I have on here is the rate determining step. The rate determining step is something you've probably not heard of before. It is known as the slowest step in any reaction mechanism, and it governs how fast the reaction can be. It's akin to that theory that you can't be any stronger than your weakest link, or you can't be any faster than your slowest step, is what this is saying. Let's go back to each of these and address whether it affects the orientation of the molecules, ions, or atoms, or whether it affects the activation energy. When we increase concentration, what we are doing is affecting the proper orientation, because if we have more particles present, the odds of our actually having proper orientation increase. With temperature, when we increase temperature, we're increasing the energy, which means our reactants start at a higher energy level, and that means our hill's a little shorter, so our activation energy is actually a little lower when we increase temperature. With surface area, we break a reactant up into different particles, many more particles than it would otherwise exist as, and we have a greater chance for them to be in proper orientation to each other to be able to react. The presence of a catalyst lowers activation energy, so it actually provides a different pathway for the reactants to follow, and that hill is actually starting at the same point as the reactants would normally start, but the hill's shorter, so the apex of the hill is actually not as high. And then rate determining step is a little different. It has an effect on the activation energy, but I'd say it also has an effect on proper orientation, so it's a little different one. What we're going to get into is the concept of rate law. A rate law actually relates the rate of a reaction as a function of the reactants. It uses the concept of the change in concentration to determine different components of the reaction. So there are two types of rate laws. They are differential and integrated. We're going to focus on differential in this particular podcast. In an upper level chemistry course, I do both differential and integrated, by the way. But seeing as some of you may not have done any integration in your math classes, I don't want to get into that at this point. The units of rate are always going to be moles per liter second unless I state otherwise, by the way. It tends to be a very proper unit. Moles per liter being concentration, representing the change in concentration, and then second sitting in the denominator with the liter tells us that it's a change in concentration over a change in time. So moles per liter second, with liter second in the denominator. We're going to look at differential rate law and look at just a hypothetical reaction and different ways of writing it. For the reaction A yields B, where A is a product, B, excuse me, that was quite backwards. A is a reactant and B is a product. And we're going to write what's known as a rate law expression. This rate law expression has a missing component that does not enable us to call it a rate law. And it is that rate equals K times the concentration of A, meaning in brackets, raised to the x power. K is called the rate law constant. Its units are dependent on what's known as the order of reactant. The order of the reactant, represented by the x, has to be determined experimentally. So we're going to look at how we determine order. You look at reaction rates and at concentrations to be able to determine order. We can't just look at the coefficients of the reactants like we do in K expressions and raise the concentrations to the power of their coefficients. It doesn't work in these particular reactions unless the whole reaction is the rate determining step. Unless there's only just one step in the reaction, then we can use what's known as the molecularity, the coefficients, to determine the order. Otherwise, we are going to determine it experimentally. Alrighty, let's look at 3 different order values because these are the most common ones seen. However, order can be any number, any integer you want to come up with, essentially. So, if the rate doesn't change when the reactant concentration is doubled, then we say that the order is 0. And if the order is 0, that means we have an exponent that's 0. You guys should recall that when you raise anything to the 0 power, it is 1. So if I write my rate law expression and plug in 0 for x, then I have rate equals K times the concentration of A to the 0 power. Well, that means that rate really equals K times, what do you think, 1? Yeah, it is 1. That means rate equals K. Well, what's K? It's a constant. That means the rate is constant. And that tells us that the rate will not change if we change our concentration. This is going to make a little more sense when I show you examples. Another order that is very commonly used is to look at the fact that the rate doubles when a reactant concentration is doubled, or the rate quadruples when a reactant concentration is quadrupled. In other words, whatever the reactant concentration does, the rate does. And if that's the case, then we state that the order of that reactant is first order. And it means that the rate of reaction is dependent on the concentration of the reactant, since it changes as the concentration changes. We would write that rate law, as opposed to a rate law expression, by filling in x with a 1. So rate equals K times A to the first power. All right, and then the third one that I'm going to give you is the next most popular order, I guess, that is worked with, and that is that if a rate quadruples when the reactant concentration is doubled, that means that the order is second order. Or if when the rate is tripled, then when the reactant concentration is tripled, then the rate would be 9-tupled, or whatever the proper oopal is of that. That tells us that the rate is dependent upon the square of the concentration of the reactant. So we write that rate law, not rate law expression. Again, the difference between an expression and the actual rate law is that we know the order. We would write that rate law as rate equals K times the concentration of A squared. Concept that I want to get in your heads is the concept of overall order of reaction, because it kind of allows us to cheat, by the way. So it seems like a silly thing to calculate because it's so easy to calculate, but I'm telling you it'll make your life easier when you're doing a little calculation of units in just a bit. So the overall order of reaction is defined as the sum of the individual orders. When, for example, rate equals K times the concentration of A to the 0 power, there's nothing to sum. It's just 0. The overall order is 0. When rate equals K times the concentration of A to the first power, the overall order is 1. But if we had differential rate law for a reaction A plus B yields C, and we had determined that the order of A was first and the order of B was second, then our rate law is rate equals K times the concentration of A to the first times the concentration of B to the second. The overall order is 3. So now I want you to think about what the units of K have to be in this reaction. Well, let's go through this together. The units of rate are moles per liter second, unless otherwise stated. Well, I'm not stating otherwise. The units within brackets are moles per liter. As I've taught you in equilibrium reactions, brackets imply molarity or moles per liter. So in essence, what I have on the right side when I consolidate is K times moles cubed over liters cubed. Well, if I isolate K and divide both sides by moles cubed over liters cubed, I end up with liters squared per mole squared second. Yes, again, liters squared per mole squared second. Now, let me give you the cheating way to do that, and that is the overall order minus 1 gives you the power of liters over moles, and then always times second in the denominator. In other words, it gives you the power of the liters and the moles. So if my overall order is 1, then 1 minus 1 is 0, and that means I have liters to the 0 over moles to the 0 second, which means I really have 1 over a second. If my overall order were 4, then I would have liters cubed over moles cubed second. And yes, I can have negative numbers. If my overall order is 0, then I have liters to the negative 1 over moles to the negative 1 second. And if you guys think about that, that means I really have moles over liters second. Alrighty. What we're going to go over now is a differential rate law problem where you calculate the orders of the reactants. And I have iodide ion reacting with hypochlorite ion to form hypoiodite and chloride ion. I've given you 5 trials. The initial concentrations of iodide and hypochlorite, the little 0 subscript there tells you that it's initial or original concentration. And then the rate in moles per liter second. What we're going to do is go through the methodology of solving this problem. The first thing I'm going to ask you to do is determine the differential rate law, which means we need to find the orders, and then determine the overall order of reaction, which means we'll add all of our orders of reaction together, both of them that is, and then I'm going to ask you to determine the value of the rate law constant with its proper units. So I've just taught you how to get your cheating way of getting proper units of K. Hope you get to use that one. Alrighty, so the way to work through this problem is to compare 2 trials. And what you want to do is use a rate law expression, meaning a variable for the order, of trial 1 and compare it to another trial, for example. And what we wish to do is isolate one order at a time. So I want you to find 2 trials where the concentration of hypochlorite ion is held constant. And then we're going to plug into our rate law expression for this reaction. The rate law expression for this reaction is rate equals K times the concentration of iodide ion to the X power times the concentration of hypochlorite ion to the Y power. The reason they're different variables is because we're not guaranteed to have them be the same order. So just make them different variables. Now, in you're looking over your data, you should see that trial 1 and trial 2 have the same concentration of OCl1 negative. So let's use trial 1 rate law expression and divide by trial 2's rate law expression. And we're going to plug in our numbers. So again, our rate law expression is rate equals K times I1 negative to the X concentration times OCl1 negative concentration to the Y. I plug in what I know, and for trial 1 I have 0.0791 equals K times 0.12 to the X times 0.18 to the Y over 0.0395 equals K times 0.06 to the X times 0.18 to the Y. Well, this becomes actually not a bad problem. It might look nasty to you, but I want you to notice that K, though unknown, is a constant, which means it divides out. So go ahead and put slashes through your K's. And 0.18 to the Y divided by 0.18 to the Y, regardless of what Y is, will divide out as well. So that leaves us with 0.0791 equals 0.12 to the x over 0.0395 equals 0.06 to the x. Well, what you do once you simplify that division is end up with 2.00 equals 2 to the x. And you should have learned in your Algebra 2 class by this point that when you have x as an exponent, you can solve for x by using log base 10. So that if you take the log base 10 of both sides, you will get x as a multiplier. So when I have 2 equals 2 to the x power, I take the log base 10 of both sides, I will have log of 2.00 on the left side equals x times the log of 2 on the right side. I then isolate x, and I have the log of 2 divided by the log of 2, and you don't even need to do that in a calculator, obviously. The log of 2 divided by itself is 1. So that tells us that x's value is 1. We now know the order of the iodide ion. Well, when I want to find the order of the OCl1 negative ion, I do the same thing, but I want to hold the concentration of iodide ion constant. So I find 2 more trials that hold the concentration of iodide ion constant. And as you look at your data, you should see that trial number 3 and trial number 5 hold the concentration of iodide ion constant, which means that we're going to plug into the rate law expression again, but using the data from trial 3 and dividing by the data from trial 5. So I will have 0.00988 equals k times 0.03 to the x times 0.09 to the y, divided by 0.00329 equals k times 0.03 to the x times 0.03 to the y. Again, I get to cancel my k's because they are constant, and this time I get to cancel 0.03 to the x because 0.03 to the x divided by 0.03 to the x is indeed 1. And that leaves me with 0.00988 equals 0.09 to the y divided by 0.00329 equals k times, scratch that k, sorry, equals 0.03 to the y. When I simplify, I have 3.00 equals 3 to the y. Again, take the log base 10 of both sides, and you have log of 3.00 equals y times the log of 3. I made this too easy for you, I know. And the log of 3 divided by the log of 3 is, again, 1. So x is 1 and y is 1. We now can write our rate law. And when we write our rate law, we simply plug in our orders. So our rate law is rate equals k times the concentration of iodide ion to the first times the concentration of hypochlorite ion to the first. My next question was, what is the overall order? Well, I simply add my individual orders, and 1 plus 1, at least when I was in school, I think it's still the same, yes, is 2. That answers question B. Question C was, what's the value of the rate law constant with its units? So I simply choose a reaction and plug in what I know. Well, I believe that I chose reaction 3, trial 3, on this particular slide, and I plugged in 0.00988 moles per liter second equals K times 0.03 moles per liter to the first times 0.09 moles per liter to the first. And I keep my units throughout this, but I'm telling you, you can do that snaky overall order minus 1 thing, and it's going to work for you. So as I go about solving for K, I end up getting the value of K to be 3.66, and its units are liters per mole second. If I'd done the cheating thing and done overall order minus 1, overall order was 2, remember. 2 minus 1 tells us my power of liter in the numerator is 1, my power of mole in the denominator is 1, and second is always sitting in the denominator. So my value of K is 3.66 liters per mole second. Now, I could have used any of those 5 trials to have gotten the same information. Because it's a constant, it really should be constant among the 5 trials. You might have a little variance, but I'm telling you, it doesn't matter which one you use. It's going to work out. Okay, so I'm going to give you one more problem to work, but I'm not going to go through it bit by bit with you. I'm just going to tell you we have A plus B plus C yields some products. Yeah, I didn't feel like finding a real reaction for you. And I've given you trials 1 through 5, the original concentrations of A, B, and C, and their rates of reaction. I'm going to ask you to do the same things I did for the last problem, and I am just going to tell you that rather than having x and y in your rate law expression, you're going to have x, y, and z. Or g, I don't care. Use whatever fun little symbols you want to use. You know, stars, flowers, whatever. Just make them different because you're not guaranteed to have them all be the same. Again, I want you to determine the differential rate law, which means you have to find their orders through experimentation. When you're looking for one substance's order, you need to hold, in this case, two substances' concentrations constant. Again, when you're looking for one substance's order, you need to hold the other two substances' concentrations constant. The second thing I want you to find is the overall order of reaction. Add all three orders together. And the third thing is the value of the rate law constant with its units. Pick any of the 5 reactions and see what you get as the value of K. If you want to stop the podcast now and do that work, that's great. If you want to keep going, then I'm about to give you the answers to that last problem I gave you. And you should find that your order of A is 0.5, your order of B is 0, and your order of C is 2. Yes, you can have any value you can dream up as an order, by the way. So my rate law, the answer to A, is rate equals K times the concentration of A to the 0.5 times the concentration of B to the 0 and times the concentration of C squared. Now since B is raised to the 0 power, you could actually leave B out if you wanted, so that it really was not there at all. But I get a little persnickety about it, and I like to see things even if they're raised to the 0 power. The answer to B I get by adding my orders together. So 0.5 plus 0 plus 2 gives me 2.5 as my overall order. And then I use that to get my cheating method. And when I plug in to one of my trials to solve for K, I find that K in this particular reaction is 0.0036 liters to the 1.5 power. Yes, you can do that. Divided by moles to the 1.5 power second. Alrighty. Just got a few more slides, and we're going to talk about reaction mechanisms. Since I mentioned that a little bit ago with the rate determining step, I need to go over that in a little more detail. And the concept of a reaction mechanism is that most reactions don't occur in a single step. They occur in a series of steps, and we call those steps elementary steps. If you've looked at Hess's law, which my students have looked at before, we've already dealt with elementary steps and seen that some reactions don't occur in just the way we see it as one reaction. The sum of the elementary steps has to give the overall reaction, by the way, so that when we add up left side of every elementary step and add up the right side of every elementary step and cancel what we can and combine what we can, we get the overall reaction. Well, within a reaction mechanism, you can have things called intermediates and catalysts that end up getting canceled when you add your elementary steps together. Intermediates are substances that are formed in one elementary step, meaning they're products in one elementary step, and then they're consumed in a subsequent elementary step. And what that means is they're used as reactants in a following elementary step. Rarely do we have intermediates part of a rate law. It can happen, but only if the rate determining step is first. Catalysts are classified as substances that are added to a step that are also produced in a subsequent step. So it's kind of the opposite. Intermediates get spit out of one step and then eaten up, meaning as reactants in a following step. Catalysts start out as reactants in one step and then in a following step get kicked out. Again, they are rarely part of a rate law as well, only if they are part of the rate determining step and that rate determining step is first. Again, the rate determining step is the slowest step. It is the only time that the differential rate law can be written by looking at a reactant's coefficients. It's the only time. So what we've been assuming with all of the equilibrium reactions that we've been doing in K expressions is that they are rate determining steps, and that was an okay assumption at that point. So let's just look at one reaction mechanism. I give you steps 1, 2, and 3 here, and I say out to the side fast, slow, and fast, and literally that is how we do reaction mechanisms. They are labeled as fast, slow, or fast. So, G, I want you to give me the overall balanced equation. That means add all reactants of steps 1, 2, and 3 together, and then put a yield sign, add all products of steps 1, 2, and 3 together, and then cancel what you can, and you should be able to come up with an overall balanced equation just by doing that. I want you to tell me what the differential rate law is, and that means you're going to look at the slowest step and write the rate law looking at the number of moles of those reactants you have. But I want you to be careful. If you have an intermediate or a catalyst in that slow step, since it's not your first one, you're going to need to make a substitution of the reactant from which it came. So you'll see that in my answers in just a moment. And then I want you to tell me what substance or substances act as intermediates or catalysts. You might turn the podcast off at this point and think about doing that, or you're welcome to just go ahead and go through my answers. It's your call. Alrighty, my answers to what is the overall balanced equation happen to be 2 moles of IBr gas yield 1 mole of Br2 gas plus 1 mole of I2 gas. Alrighty, so my answer to what's the differential rate law means I look at my slowest step and I'd like to write rate equals K times IBr to the first times Br to the first. And then I'm done. However, I'm not really done because Br is not in my overall reaction. Something that's not in my overall reaction is not going to be in my rate law unless that something is in the very first step. And it's part of my slowest step, which is my very first step. Well, I see that the Br really is a product in my first step and it's a reactant in my second step. So the first step is fast, and that really means I get to make a substitution of Br. And I substitute it with the substance that made it. It's that simple. So that means the Br that's a reactant in step 2 really came about very quickly from the decomposition of IBr in step 1. And that means that I get to write IBr times IBr, right? So I consolidate and have rate equals K times IBr's concentration squared. Again, I substituted the IBr for the Br. And then the answer to my third question, what substances act as intermediates or catalysts? Well, remember, an intermediate is a substance that is a product in one reaction and then in some following reaction, not necessarily the next one, it's a reactant. So if I look for intermediates, I have I that you see is produced in the first step and then consumed or reacted in the third step. So that makes it an intermediate. And you canceled it out because it was equal number of moles on each side. I also see that Br is produced in the first step, as we've already analyzed, and then consumed in the second step. So it's also an intermediate. I do not see any substance that is a reactant in one of the steps and then in a following step is a product. Therefore, there is no catalyst in this particular reaction. Alrighty, that about sums it up for our kinetics. I'm going to have a little practice sheet that I have you do in class for those of you who have me, and we'll just have fun with this. Okie dokie. Look forward to doing the next one for you. I think it will be on redox reactions, which are a blast. I absolutely love those. So y'all be sure and come back to listen to me. We'll see what we can do. Thanks. Bye. I almost forgot. Hey, we got to have a joke, don't we? Okay, 2 atoms walking down a sidewalk. One of them bumps into a tree and goes, "Hey, I lost an electron." The other one goes, "Are you sure?" He says, "Yeah, I'm positive." Get it? Positive. It's because he lost an electron. Have a good day. Bye.